Hello everyone, and welcome to the next webinar series. This is our inaugural webinar, and we will be conducting webinars every fourth week of the month. So please stay connected for upcoming sessions. I am Aparna Deshmukh, Technical Director with Next, and I will be your moderator for today's session. We are thrilled to dive into our first webinar titled Practical Utilization of New ACI Code 440.11 on GFRP Reinforced Concrete Manuals for Engineers and Contractors. A PDF of this presentation can be found in the handbox. You can use the PDF to follow the presentation and take notes if you desire. You may use the question box to ask questions during the webinar, and we will do our best to address them at the end of the presentation. For continuing education credit, attendance for the entire duration of today's live webinar will earn you a certificate of completion for 1 PDH. Your certificate will be available in ACI University under the Certificates tab within 2 days. For those who cannot join us live, the on-demand recording will be made available about a week after the live presentation. ACI is an approved education provider for the American Institute of Architects and the International Code Council, and this webinar has been approved for 1 learning units. Let's get started with a short description of our today's webinar. This webinar will focus on providing useful guidance for engineers and contractors interested in utilizing GFRP bars, with special emphasis on the new manual available for designing and installing GFRP reinforced concrete. I hope these valuable resources will help you familiarize with the use of GFRP bars in your projects. Our learning objectives for this webinar are as shown on the screen. Now, I would like to introduce our speaker, William Gold. He is Senior Engineer at American Concrete Institute. Prior to joining ACI, he was with the Master Builder Solutions for over 20 years. He brings a depth of experience in the use of fiber-reinforced polymer composite materials to reinforce concrete and masonry structures for both new construction and repair. Will has been an ACI member for many years and is a fellow of the Institute. He is past chair of ACI Committee 440 on FRP reinforcement and currently serves as the secretary of ACI Committee 440S, which is focused on developing the code for FRP strengthening systems. He is a registered professional engineer in the state of Ohio. Let's welcome Will and listen to his presentation. Please take it away, Will.
Thank you, Aparna. Thank you for that great introduction. It is truly an honor to be the inaugural speaker in this webinar series presented by NEX. I would also just like to thank all of the participants and attendees today. It looks like we have a lot of attendees live on the webinar today. Thanks everybody for taking some time today to learn a little bit about non-metallics in construction. When I first started thinking about this whole topic that NEX is focused on, which is the use of non-metallic materials in construction, I really started thinking about, if I were someone who had never used non-metallic materials in a structural or in a construction type application, really where would I start with that and where would I feel comfortable? And I think the topic that we're going to talk about today is really where I would start. I would really start focusing on using GFRP reinforcement for reinforced concrete. And the reason that I say that is that I think that with this particular topic, all of the things now are really in place for the use of this material in a safe, in a responsible, in a practical, and an economic way. And I think that everything that I would need to be comfortable using this material in a construction type application really are out there right now. And that's really what I want to try to convey with the with the topic today. I really want to convey where we are with GFRP reinforced concrete and how we can practically utilize it out in the construction field. So the topics today that I'm going to cover, if you're not familiar with non-metallics or what we call FRP materials, I'll give a quick introduction to FRP materials just so that we're all kind of level set in terms of the topic. And then I'll talk a little bit about the applications of GFRP reinforcement specifically for new construction. And then we'll talk about some of the resources available where, again, it's very practical to now go out and really use this type of reinforcement in day-to-day construction type applications. And again, I think that this should serve as a kind of a launch pad for other webinars that Next is going to be sponsoring in the future. And I really look forward to some of the other discussions that we have around non-metallics. But I think this is really a great place for us to kind of get started with this whole topic. So with that, starting off just about FRP materials in general. FRPs, they go by many terms. We sometimes call them composites. We certainly refer to them as non-metallic types of materials. What we're talking about when we talk about FRP specifically are fiber reinforced polymer materials. And these basically are exactly as their name describes. So you have a polymer, or a more basic term is plastic material, that is reinforced with a high strength fiber reinforcement. The polymers and the fibers can be any number of different types of materials. Generally speaking, the fibers that we talk about are carbon fiber and glass fiber. We also talk about basalt fiber, which is similar to glass, just a slightly different chemistry. So there are several different types of fiber that we talk about. And we also talk about different types of polymers that are used in these materials. These materials are all using, though, continuous fibers. So I make a point of this because the fiber material that's reinforcing these materials are all continuous throughout the entire length. This is not to be confused with fiber reinforced concrete, where you might have discrete chopped fibers that are kind of distributed in a concrete mix. This is a completely different animal. This is continuous fibers that are reinforcing this material along its entire length. And it really gives this material very high-end structural properties. And because of this, you see a lot of use of this type of material in a lot of different types of applications outside of the construction realm. So aerospace is one of the primary ones where you see a lot of use of this material. That photo in the lower left-hand corner is the Boeing 787 aircraft. That aircraft uses FRP materials in virtually every structural element of that aircraft. So the fuselage, the wing structure, all of these things are fabricated from a carbon fiber reinforced polymer material. You also see these types of materials in different types of applications like sporting goods, things like carbon fiber bicycles and golf clubs, hockey sticks. All of those types of things are very common uses of FRP. You also see them in shipbuilding. There's a photo there of a glass fiber reinforced hull of a sailboat. Fiberglass types of sailboats and marine type structures like that are very common nowadays. So what I would say is that we really do encounter these materials pretty commonly day to day. We're not as experienced in using them maybe in construction, but certainly in day-to-day applications, these materials are becoming more and more common. When we talk about the use of FRP for concrete, one of the primary uses, again, is in the use of GFRP, or glass fiber reinforced polymers, as an alternative to steel reinforcement in concrete. So you see some of the photos that are there. These photos, the bars themselves, they kind of look and feel similar to steel reinforcement that you might see in concrete structures. But instead of steel, these are a non-metallic alternative. These are GFRP bars that are used in these applications. So they're used in a very similar fashion to steel, but materials themselves are quite a bit different. So that's really what we're going to talk about here today, is the use of these GFRP reinforcing bars as a way of reinforcing concrete in new construction. So before we get too far down the path of talking about GFRP reinforced concrete, we do need to start with kind of a fundamental understanding of how these materials behave. And we could probably spend quite a bit of time talking about all the different properties of FRP materials, how they behave. You can take entire courses on FRP material properties and how FRP material properties work. But really, I want to focus on just a couple of key aspects of FRP materials that you really have to understand in order to use this material to reinforce concrete with it. So the first and foremost being just general tensile properties. How do these behave in tension? And in tension, these materials are very high strength. Generally speaking, they are multiples of the strength of steel. They are 2, 3, 4, 5 times stronger than steel, depending on the materials we're talking about. But generally speaking, they are less stiff than steel. Their modulus of elasticity is lower. We do kind of pay for the high strength of these materials, though, with ductility. These materials are 100% linearly elastic right up until failure. There is no yield plateau. There is no strain hardening or strain softening. There is no plastic behavior whatsoever of these materials. They take load and they take load and they take load, and then suddenly, without really any warning of failure, they suddenly rupture. So you can see that kind of illustrated in the graph down on the lower right. In that graph, the blue line is the behavior of a typical GFRP reinforcing bar, and the red line is the behavior of a typical steel reinforcing bar. So the GFRP bar is quite a bit stronger than the steel rebar is, but it is less stiff than the steel rebar is, and steel has a nice defined yield plateau followed by some strain hardening. GFRP has none of that, is 100% linearly elastic up until failure. If we were to plot a carbon fiber or a CFRP bar on that same chart, you would see much the same. The CFRP bar would be quite a bit higher even in strength than the GFRP bar, and would be closer to the modulus or the stiffness of steel, but still a little bit less stiff than the steel reinforcement that we typically use. The third point that's there on the slide is that FRP materials do exhibit anisotropic behavior. So this means that they have different properties depending on which direction you're looking at. So if we look at the strength of the material that's kind of depicted in the little diagram down on the left, that material would have a very high tensile strength in the longitudinal direction or in the direction that the fibers are running, but it would have very low tensile strength in the direction perpendicular to the fibers. So it's kind of similar to wood in that it has kind of a grain, if you will, has high strength in one direction, low strength in the opposite direction. And that's really because the fibers are dictating what the strength of that material is. The polymer itself has relatively low strength. The fibers are really the thing that dictates how strong that material is. But beyond strength, the other properties of the material also vary depending on the direction you're looking at. So strength varies depending on the direction, but so does modulus of elasticity. So does things like thermal conductivity and electrical conductivity. And so do things like coefficient of thermal expansion. So I mention these because these are kind of important when we start thinking about using this as reinforcement for concrete. All of the properties of the FRP rebar are kind of in the long direction of the bar itself. When we start looking at actions that are perpendicular to those fibers, such as shear in the bar, those properties are going to be lower. The other thing to consider with FRP bars is that they have a coefficient of thermal expansion that's very similar to steel and concrete when you're talking about the longitudinal direction. But in the transverse direction, the coefficient of thermal expansion is actually quite a bit different, and it's quite a bit higher. So we have to start thinking about how do we mitigate potential issues with bars being inside concrete when we have temperature fluctuations. So all of those types of things we have to start thinking about when using FRP bars for reinforcing concrete. The last point that's up there is that the resins themselves do soften at high temperatures, and the temperature thresholds are fairly low. So most of the resins that are used in a commercially available GFRP bar will start to soften at a temperature of around, say, 250 degrees Fahrenheit. So a fairly low temperature threshold for these bars. That obviously has a lot of implications when we start thinking about things like fire resistance or applications that are in high service temperature environments. So again, we have to start thinking about these types of things when we're using these bars for reinforcing concrete. So as we start thinking about reinforcing concrete, I just want to show this photo. This is actually a photograph of not a steel reinforced concrete, but a steel reinforced masonry wall, but I think it illustrates the point very well. So this masonry wall, which you can see here, is bowed pretty significantly. So that wall is right now resisting load applied to it from this spreader bar here that's putting load into the wall, putting lateral load into the wall. So as that wall appears now, I can't really tell whether that wall is right at the cusp of its failure mode or whether it has a little bit more load to resist. Again, you can't really tell with FRP reinforcement because it doesn't have a defined yield plateau. We don't know exactly when the failure is actually going to occur. But what I can tell about that wall is that it is deflected quite a bit. There is quite a bit of deflection that we see in that wall right now. And this is pretty characteristic of FRP reinforced elements. They do exhibit a lot of deflection prior to failure. So even though they don't give a lot of warning of failure, they do have pretty large deflections and pretty large things that look a little bit, call it scary, before they do fail. The other thing that you'll notice is that the joints in the masonry have opened up quite a bit. So this would, if this were reinforced concrete, this would translate to crack width. And this is another pretty characteristic thing of FRP reinforced concrete or masonry, is that we do see very large crack widths develop with FRP reinforcement. So again, this gives us a pretty good idea of how these materials are going to behave when we use them as reinforcement. So the last thing that I'll show with this, which is actually a video, is that once you do actually remove the load from this wall, after those loads are removed, the wall basically snaps back to where it was originally. Again, these are linearly elastic materials, so as soon as you remove the load, they go back to their original unloaded position. So you see very little residual deflection in members like this. Again, all very characteristic of what we now know of as how FRP reinforced structures behave. Okay, so we've talked a little bit about FRP materials. Now, why would we actually use these to reinforce concrete to begin with? And if you look back at the history of the use of FRP to reinforce concrete, this is really something that has been considered and has actually been done for many, many decades, going back to probably the 1970s. And really the initial thought behind using FRP for reinforcing concrete is because we did not want concrete structures that looked like this. So if you live in an area, maybe a coastal area that's exposed to a lot of salt water, or if you live in a northern climate where a lot of de-icing salts are used on roadways, reinforced concrete starts to look like this, and maybe, hopefully it doesn't look quite as bad as this particular structure does. This is a pretty extreme case, but we have seen historically a lot of corrosion of reinforcing steel in existing reinforced concrete structures. So the initial idea behind using FRP reinforcement was really, can we extend the life of these structures? Can we get away from some of these corrosion-related issues by using reinforcement that is completely non-corrosive? And in fact, FRP reinforcement is completely non-corrosive. It will not corrode. So potentially we have the opportunity to extend the lifespan of these types of structures by using this non-metallic, non-corrosive type of reinforcement. And in fact, we have done that. We've done that in many, many structures over many, many years. We use it a lot in concrete structures that are in very highly corrosive environments. Things like, again, bridge decks, where they are in a northern climate where de-icing salts are used. Concrete bridge decks experience a tremendous load of chlorides when those de-icing salts are used, which leads to corrosion. By using a non-corrosive reinforcement, you can dramatically reduce the maintenance on these concrete bridge decks, and you can extend the life of these structures by using FRP reinforcement. So this has been done in a lot of different places around the world to try to mitigate these effects of corrosion, limiting the lifespan and increasing the maintenance of concrete bridge decks. But not just bridge decks, other structures that might be exposed to de-icing salts, like walkways, parking garages, where cars might be bringing in de-icing salts into the garage. Those are all places where FRP reinforcement starts to make sense and has been used in the past. And then also when we look at coastal areas, again, coastal areas are exposed to a lot of chlorides. They are a very corrosive environment. So the photo that you see there is of a reinforced concrete seawall being right next to the ocean. This wall is exposed to a tremendous load of chloride. And by using FRP bar instead of steel rebar, we can help increase the lifespan of those structures pretty dramatically by using non-corrosive types of reinforcement. And then if we talk about the economics of this, as it is today, FRP reinforcement is pretty competitive from an economic standpoint as well. It can vary depending on exactly where pricing falls, but generally speaking, FRP reinforcement is less expensive than using stainless steel reinforcement, can be competitive with using things like galvanic steel or epoxy coated bar, and can even be competitive with using better concrete to help solve the corrosion problem, like using corrosion reducing admixtures in the concrete or denser concrete. FRP can start to make economic sense over some of these other alternatives, just depending on the nature of the project and what all is involved. So they are now becoming a little bit more commonplace in these types of applications. The other place where FRP has been used historically is really for applications where a reinforcement that is either non-conductive or electromagnetically transparent is needed. And these are kind of specialty applications, but they are applications like the photo that you see there of an MRI unit in a hospital. These MRI units in hospitals have limitations on how much ferrous material or metallic material can be around the magnet that's used in these. So FRP reinforcement is a really good alternative where you need to reduce the amount of ferrous or magnetic material around these types of units. Other applications in near high voltage equipment, near navigational equipment around airports. There are specialty applications where FRP reinforcement is really about the only way that you can reasonably reinforce concrete and avoid some of the interruption that would be caused if you used a metallic type of reinforcement. But all of that aside, I would say that really right now in 2023, the most common use of FRP is not necessarily because it's non-corrosive or it's non-conductive, non-metallic. A lot of the use of FRP is really driven by just plain productivity. FRP reinforcement is really to a point now where it is in a lot of cases favored by contractors because it is so easy to install. I remember when I was first involved in the use of a GFRP for reinforcing a concrete bridge deck, I remember the contractor placing the bar. He wasn't really concerned with the fact that the bar was non-corrosive and that it was going to extend the lifespan of the bridge. What he was most excited about was the fact that this bar was so lightweight, it was so easy to use. The workers loved using it because they weren't nearly as fatigued at the end of the day by lugging rebar around. It really is a much easier material to use to reinforce concrete in a lot of cases, and it really can improve productivity. So a lot of the use right now is really driven by reducing the cost of a particular project based on improvements in productivity versus anything else. So one of the drivers for this is the fact that FRP, again, is very lightweight. So you see up on the slide, GFRP bars are 1/3 the weight of a steel bar. And just to put that in practical perspective, a 30-foot long number 5 GFRP bar weighs about 9 pounds, whereas the comparable steel bar weighs 30 pounds. So you can see the photo there, that person is carrying a bundle of about 15 number 5 bars. It'd be very difficult to lift that if that were the same thing out of steel. It would be 3 times as heavy. So when you multiply that across working with reinforcement like this over the entire course of a day, this really does improve productivity. It reduces worker fatigue. It reduces repetitive stress on workers. So it really is a much easier material to work with than steel reinforcement in a lot of these applications. Then we can also start thinking about transportation cost. Reducing weight does reduce transportation costs, which again is vital and beneficial. In some applications where you have difficult access, you can get bars to places more practically than you can with an equivalent type of steel bar. And then just general handling characteristics. The bars are a lot easier to cut through than steel. They cut more like wood than steel. There's no sparks that are generated when you cut through the bar. They cut through, you can cut through the bar fairly easily. So they're much easier to handle from that standpoint. And they're just easier from general handling on the job site. So if it's a really hot, sunny day, the bars don't become excessively hot to the touch, or if it's a very cold, icy day, the bars don't get really cold to the touch. So unlike steel rebar, which is conductive, these bars are not conductive. So they do tend to be easier to handle in excessively hot or cold conditions. So just a couple of quick examples of projects where FRP rebar has been used. This is a hiking and biking trail that's down in Houston, Texas, that was done last year. This project is a very long concrete mixed-use trail, and this trail goes through a fairly remote area. There's not a whole lot of access with large vehicles and that sort of thing to access the site. So FRP reinforcement in this application made a lot of sense. Workers could tie rebar cages and carry them by hand down along the trail and place them in a very cost-effective, economical way. This project, this is actually the largest project, largest single use of FRP reinforcement currently. This is a flood mitigation channel in Saudi Arabia. There's a really nice article on this project in the October 2021 edition of CI that really kind of breaks down the cost comparison of using FRP versus steel reinforcement. And here, non-corrosive properties of the bar were important, but at the end of the day, the cost savings involved in using FRP was really the main driver. And again, that article has a really nice breakdown of how that worked in this particular project. So again, very nice application of using FRP reinforcement. And then here's another project, this one down in Charleston, South Carolina. This is a seawall similar to what we saw earlier. So the non-corrosive nature of FRP was pretty critical. But again, even more than the non-corrosive nature, the contractor really fell in love with the handling characteristics of FRP bar. So there is another nice article in CI on this project back in November of last year. And here the contractor just realized how much more productive they could be with FRP rebar versus steel rebar in this project. So again, highlight some of those some of the more modern thinking about using FRP rebar to boost productivity and not just for some of these other attributes that FRP brings to the table. Okay, so what I want to spend a little bit of time talking about then are some of the resources that are available to go out and use this type of reinforcement on project sites. One of the drawbacks that I would say of FRP reinforcement is that it is admittedly more difficult to engineer than steel reinforced concrete is. A lot of us are very familiar with designing steel reinforced concrete. Using FRP does require learning a lot of new design concepts, and the design process itself is more involved when we're using FRP, and I'll show you some examples of why that might be. So we've tried to build up some resources to make sure that we know how to design it and we can design it appropriately. What I always say is that from my perspective, or in my opinion, if I can spend a little bit of time sitting at my desk behind a computer screen designing something to help the contractor out in the field be more productive, that is definitely time well spent. So I think that we can spend a little bit more time designing FRP reinforcement so that people out in the field have a little bit easier time installing reinforcement. And again, I think that's pretty good time spent on the engineering side. The other point that I want to make, and the point that I made at the onset of this presentation, is that with GFRP reinforced concrete, all of the things are in place now for using this material in a very appropriate and responsible way. And these are the highlights of that. We have material specifications for FRP reinforcement. We have construction specifications, and now with the publication of ACI code 440.11, we have building code requirements for FRP, and then we're also backing that up here in the very near future with some good practical guidelines for the use of FRP reinforcement. So what I really want to spend a little bit of time talking about are these resources that are now available and how they can really help us utilize this material and utilize it in a practical way out in the job site. So the first resource is this material specification ASTM D7957. So FRP materials in general is a fairly complicated subject. It is a lot to know. There's a lot that goes into FRP materials, the quality of FRP materials, what types of fibers should be used, what types of resins should be used or polymers should be used, how it should be manufactured, what material properties should be, what durability should be. All of those things are complex, and there's a lot to know. But at the end of the day, where we are at right now is we have a material specification which specifies all of the minimum properties for FRP bars. So this material specification really allows engineers and designers to use this standard specification and specify, as long as the bars meet ASTM D7957, then they are appropriate to be used on a project site. And that's really where the state of the industry is right now. As long as you can meet this material spec, it's appropriate to use all the other ACI documents relative to reinforcing concrete with FRP. And these are bars of a sufficient quality to be used on construction project sites. So sorry, I skipped ahead. One of the couple of key points to understand about this material specification, though, is that it is very specific. It is only for GFRP, so only glass fiber reinforced bars, and it is only for bars that are made using one specific type of resin. And that's based on our experience with this particular type of bar. It's also only for solid round GFRP bars. It's not for bars that are other shapes. It's not for hollow bars, which do exist. It's only for solid round GFRP bars. It is important to know that even though the material spec is fairly specific, you might see bars that look a little bit different. So in the photo there, you see a couple of different varieties of FRP bar. All of these bars would meet the ASTM spec, but they do look a little bit different based on their surface treatment and maybe based on their color. So there might be different colors of bar, there might be different surface treatments, but these do all conform to the ASTM spec. The ASTM specification does have minimum bond strength requirements, so all these bars have to meet that, and they do that with different surface treatments like ribs or like helically wound fibers or grooves that are cut in the bar. So they may look a little bit different, but all of these do meet the ASTM spec for bond to concrete. The other thing that I'll mention is that we're trying to make the spec as easy as we can. So the bar sizes that are specified by ASTM are the same bar sizes, same standard bar sizes as steel bars. So we have number 2 bars through number 10 bars. The area of the bar, the diameter of the bar is the same as the equivalent bar. So a number 5 steel bar is the same diameter and size as a number 5 GFRP bar. So all of those things are the same. The one thing that you should note about GFRP bars, though, is that their strength does vary based on the bar size. So smaller bar diameters generally have higher strength than larger bars because of the way that stress is kind of distributed throughout the cross section of the bar. So there are different minimum strength properties in ASTM based on what bar diameter you're looking at. So it's not like steel that one size bar, the strength is 60 KSI, and if you move to another size bar, it's still 60 KSI. These bars do vary based on the bar diameter. So then we also have the construction specification. So in addition to the material spec, we have a construction spec. So the construction spec supplies all of the minimum requirements for installing these bars out in the field. This spec is very similar to Section 3 of ACI 301, which deals with steel reinforcement for concrete, but it's revised to cover GFRP bars. And again, try to make this as simple as possible and covering a lot of the same topics, but just emphasizing the areas where specific requirements for GFRP need to be made. So just to give you a little bit of a flavor for what's in that document, not to go through this in much detail, but the bars themselves, they do have to be handled a little bit more cautiously than steel. You don't have to handle them too delicately, but they are easier to damage. So there are requirements for how you handle them and what you do if the bars are damaged. You also have to be concerned with long-term exposure to direct sunlight. Direct sunlight will eventually affect the resins or the polymers that the bars are made out of. So they do have to be protected from sunlight if they're exposed for a long term. So according to the spec, if they're exposed to direct sun for over 4 months, they need to be covered with some type of opaque tarp or plastic. Again, 4 months is a fairly long period of time, but you might have bars that are stored on site and then placed, and then concrete isn't actually poured on top of the bars for a couple of weeks or so. So you might have some situations where that may come into play. There's criteria for cutting the bars. Cutting the bars, the main thing is that you cut them using a smooth tooth saw blade, something that will cut through metal like a hacksaw or a fine tooth blade on a rotary or a reciprocating saw. The things that we want to avoid are trying to cut them by shearing or like with bolt cutters. Certainly don't want to cut them using torches, and you don't want to try to cut them by bending them back and forth. That will not cut the bar in the fashion that you want. So these are all, again, specified in the construction specification. There's also discussion of supporting the bars. The bars have to be supported by chairs. And because the bars are lower modulus than steel, you do need to use more chairs to support the bars. The spec indicates 2/3 of the spacing that you would usually use with a steel bar. Then the other note there is that GFRP bars can float in fresh concrete. So in some cases, you not only have to hold them in position from sinking, but you also have to hold them so that they don't float to the top of the concrete pour. So they may have to be secured against floating to be able to maintain the position of the concrete, or the position of the bar in fresh concrete. In terms of tying the bars, they can be tied using any methods, any of the conventional methods. If the bar is being used for a specific non-metallic purpose, so if it's supposed to be non-corrosive or if it's supposed to be non-magnetic, things like nylon zip ties or plastic bar clips that are non-metallic are preferable in those situations. But again, they can be tied with things that you tie regular reinforced concrete with as well, a regular steel reinforcement with as well. In terms of cover requirements, the cover requirements are not that much different than steel. The table that you see there is virtually identical to the requirements for steel reinforced concrete. The one caveat there that I would highlight is that in ACI 440.11 in the design code, there is some commentary about making sure that cover exceeds at least twice the bar diameter. That requirement is in there specifically to address the concern of the coefficient of thermal expansion in the transverse direction of the bar. So because the bars do expand at a higher rate, there needs to be enough cover surrounding the bar to help restrain that expansion without cracking the concrete. And 2 bar diameters is kind of the minimum that we look for to make sure that that restraint is provided. Then finally, last thing with the construction spec is bends and hooks in FRP bars. Very important note that GFRP bars cannot be bent in the field. They are, again, linearly elastic. So if you try to bend them in the field, they will just break. They won't bend the way a steel rebar will. So these hooks and bends in the bar do have to be manufactured by the FRP bar manufacturer. They're delivered to site this way. So it's really important to make sure that if there are hooks and bends that are needed, that those are appropriately detailed, that you talk with the FRP bar manufacturer about what is practical and what can be done, and then make sure that those bars are available on the job site when they need to be, because there are oftentimes lead times associated with fabricating these types of bends. So again, these have to be planned out ahead of time, and you really have to think about where these are going to be used when you do have to do details like bends and hooks in in a GFRP reinforced concrete application. Okay, so now let's talk a little bit about the ACI code for ACI 440.11. So again, we tried to make this code as easy as possible for people to kind of acclimate to. So if you're familiar with using ACI 318, ACI 440.11 will look very familiar. All of the organization of that 440.11 document is identical to ACI 318, right down to, if you look at section 7.3.6.4 in ACI 318, you will see a very similar section 7.8.3.4 in 440.11, only that code language will be changed slightly to accommodate GFRP reinforcement. So everything is meant to correlate very well with ACI 318. And again, that's really intentional so that somebody familiar with 318 can pretty easily navigate the building code for using GFRP reinforced concrete. An additional note there is that this code will be referenced by the IBC starting in 2024. So this will be part of the building code. And again, this gets back to what I mentioned earlier about all the things being in place to use this reinforcement out on job sites now. It is really now part of the general building code. So there are really very few obstacles to overcome to use this material on an actual project application. A couple of things about the code itself. These are the topics that the code covers. It covers beams, one-way, two-way slabs, columns, walls, foundations, connections, and the strength of existing structures. So it covers a number of different types of concrete elements. However, there are some topics that it does not cover. It does not cover the use of GFRP for lightweight concrete. There just is not enough information out there from a research perspective to include lightweight concrete at this point, maybe something in the future, but not currently. Then pre-stressed concrete, you can do things like FRP tendons. Those do exist, and those are out in the marketplace right now. However, the 440.11 code does not cover pre-stressed concrete. Again, maybe a topic in the future, but right now, as of the 2022 version, it does not cover pre-stressed concrete. Then a couple of other items like deep beams and diaphragms are not covered. Shotcrete is not covered. Anchors to concrete, either post-installed anchors or other types of anchorage to concrete is not covered in the 440.11 code. And then finally, plain concrete is not covered because plain concrete doesn't involve reinforcement, so there's no need to include GFRP reinforcement. Another important aspect from a scope standpoint is in seismic. So because FRP is a brittle reinforcing material, because it is 100% linearly elastic, the behavior in a seismic type loading situation would be quite a bit different than steel reinforced concrete. And a lot of that is not really well understood right now. So for the time being, the code limits the use of GFRP reinforced concrete to seismic design category A if GFRP is going to be used in any of the lateral load supporting elements. So anything that's resisting lateral loads, if GFRP is going to be used, it has to be only seismic design category A. In seismic design categories B and C, you can use GFRP reinforcement, but only in gravity elements. So only in beams, slabs, that type of thing. GFRP is not allowed if it is part of the seismic force resisting system and in seismic design category B and C. And then finally, if you're in seismic design category D through F, GFRP reinforcement is not permitted in any of the structural elements per the code as it stands today. And then I would just highlight that in the IBC, when the IBC adopts 440.11, it will only allow that first condition. It will only allow GFRP in seismic design category A structures. Then similarly, from a fire resistance perspective, we talked about these materials having low temperature thresholds. From a fire perspective, the fire resistance, anywhere where a fire rating for a structure is needed, GFRP reinforcement is not currently permitted by the code unless the building official allows it through either demonstration by calculation or testing that it's okay to use. So this statement is currently in the code. There is commentary in the code on how you can use FRP reinforcement in fire-rated construction. And I'll just give you a little bit of a sense for what that looks like. There are ways of getting fire ratings with FRP reinforced concrete. They're just, at this point in time, they're not well tested and they're not well validated. So this is restricted to commentary language. But essentially the idea is that if you can provide anchorage of the reinforcement in what we call a cool zone, so a zone that's outside of the fire exposure area, or if you can insulate the areas where the bar is being anchored or developed, then the other parts of the bar that are exposed to fire, they may lose the properties of the resin, but remember that the fibers in the bar are continuous, and the fibers themselves can actually resist fairly high temperatures. So the fibers are going to remain continuous in this bar when they're exposed to fire, and as long as we can keep it anchored, we can still get fairly reasonable fire ratings out of these structures. So a lot of the commentary language is really built around doing these types of things where we maintain these cool anchorage zones to help protect the reinforcement where it's being developed or where it's being spliced. So other kind of differences with the code, there are a couple of key things to be aware of when using FRP reinforcement. Again, this is a linearly elastic reinforcement, so we want to make sure that, number one, we have higher reserves of capacity, so we have higher safety factors against failure. What you can see in this diagram, the green line is kind of the M sub U, the design moment capacity that's needed. And then the black line is what we would typically design a steel reinforced concrete beam to be. And then these two lines 2 and 3 are what we would design a GFRP reinforced concrete beam to look like. So the GFRP reinforced concrete beam has to have a higher strength so that we have higher reserves of capacity before we encounter a failure of the beam or flexural member. And in fact, we slightly favor having concrete crushing control the failure because it is a slightly more, I wouldn't call it ductile, but it gives you slightly more warning of failure than FRP rupture would, or developing the full capacity of the FRP reinforcement. So the dashed line there is a concrete crushing controlled failure mode, and the darker line is a GFRP rupture controlled failure mode. And again, we slightly favor having the concrete crushing failure mode control failure. All of that being said about strength, really with GFRP reinforced concrete, serviceability almost always governs the design. So the bar modulus is lower than steel, so deflections really govern design. Either deflections or things like crack width really tend to control the design. So the design process with FRP is quite a bit different. We actually start by designing for serviceability, and then we check that strength requirements are met, which is really the opposite of what we do with steel. And then this is also complicated by the fact that with GFRP reinforcement, you have to calculate deflections. There are no tables for minimum height or thickness of a section. You have to actually calculate what your deflections are. So you need to calculate those and then compare them to limits. And again, these limits are often going to control the design, so it becomes pretty critical to calculate these types of things. If you just substitute the same amount of GFRP reinforcement in a design as the steel that's required in a design, you will get larger deflections and wider crack widths. So this is not what the code prescribes. We are requiring, in most cases, more GFRP reinforcement than steel reinforcement, just to get the meet all of the code requirements for serviceability when we're designing GFRP reinforced concrete flexural members. Because designs are often governed by serviceability, there are the modulus of the bar does tend to drive a lot of the designs. So a lot of the how many bars you end up with, the size of bars that you end up with, is oftentimes dictated by the modulus. So the 440 code does recognize this, and it allows you to design according to the minimum ASTM requirements for modulus, but it also allows you to design according to what the manufacturer's modulus is. Reason for that is that manufacturer's modulus may be higher than the ASTM minimum. The ASTM minimum is 6,500 KSI. An FRP bar manufacturer may have a bar that's 8,700 KSI in terms of modulus. So it might be beneficial to use those actual manufacturer's properties to sort of optimize how much reinforcement is needed. Again, something that the code allows, but is a key consideration. Then last two topics on the design side, shear and torsion, and also I'll touch on columns. Where we have FRP reinforcement used for shear, so things like FRP stirrups, the bend in the bar does reduce its tensile strength, so we have to account for that in design. And we also have to be concerned with the fact that the dowel action of the longitudinal bars is not going to be as high because the shear strength of the actual shear strength of the bar itself is lower than a steel bar. So that does impact the shear capacity as well. So a lot of the shear equations are different than what you will see for steel reinforced concrete because of these factors. And then for columns, the bars themselves, they do not have the same compressive strength as tensile strength. So again, unlike steel, their compressive strength is lower than their tensile strength. So to compensate for this in the design process, the bars are just assumed to have the same strength and stiffness as the surrounding concrete. So we're basically treating the bars as having the same compressive strength as the concrete that they're embedded in. So fairly low compressive strength. This does limit what we can do with FRP bars and things like columns, but those design limitations are put there intentionally because the compressive strength of the bars themselves is lower than steel reinforcement. And then finally, things like tie spacing. Ties are generally spaced tighter because there is a greater propensity for longitudinal bars to buckle, and we've got to space the ties closer in order to restrain that potential for buckling of the longitudinal bars. All right, so I just want to wrap up with a little bit of a sneak peek into two manuals that are currently under development within ACI. So we have a design manual that is currently under development now that will be published soon. This design manual is very similar to MNL 17, which is the design manual for steel reinforced concrete. And it just goes through some very detailed examples of using GFRP for designed according to ACI 440.11. So some T-beam examples, one-way, two-way slabs, columns, and so forth. Similar to MNL 17, the document is based around designing a building that looks something like this. a steel reinforced concrete building with reinforced concrete beams supported on columns and one-way slabs on one floor and a two-way slab on another floor. And I'm not going to show the details of each individual example, but I do want to give you a little bit of a flavor for what the outcome of these design examples are. The design examples were worked in conjunction with the MNL 17 examples so that you could kind of compare what does the design with a steel reinforced concrete beam look like compared to a GFRP reinforced concrete beam. So if we look at one of these elements, like this interior beam, what we would find is that they look actually pretty similar in this case. We're using one size larger GFRP bar than we are steel bar, but the overall size of the member is the same. The dimensions are equivalent. Everything looks pretty similar. There's a little bit different detailing of the stirrups, but most of this is pretty similar to the steel reinforced concrete beam in this particular case. However, in some of the examples, they are vastly different. So this is a edge beam with torsion. And in this case, you see the beam size is quite a bit larger. There's quite a bit more reinforcement that's required. And this is because this is kind of an extreme. There is no integral slab here, so the stiffness of the overall member is lower, and deflections are going to be higher. There's also, these are controlled by shear and torsion, so the overall size of the section needs to be larger to accommodate shear and torsion. So you, again, kind of see the difference between this extreme case of the difference between steel and GFRP reinforced concrete. And then if we look at columns, again, similarly, some of the details with columns are different. So we can't do things like these offset bins. We have to do different detailing of the reinforcement. But the overall size and shape of the column is the same. However, the building that is designed in the GFRP manual is a 4-story building in seismic design category A, whereas the one in MNL 17 is a 7-story building in seismic design category B. So the loads on this column are quite a bit higher than they are for the GFRP reinforced column. And this is really getting to what's practical with GFRP. There are practical limitations with what you can do with a GFRP reinforced column, so those are highlighted here. And then lastly, we do have another manual coming out that is really geared toward the installation side, using these contractors using these bars on the job site. It really goes through a lot of the details on how you place, install, tie GFRP bars. And then it's also specifically directed to a lot of residential construction. Residential construction happens to be a really common use of FRP now because it is so much easier to use than steel reinforcement. It has gained a lot of use in residential construction. But we've also included in this manual a lot of prescriptive design tables for use in common residential applications. So things like below grade concrete walls. There are tables in this manual to show you the size and spacing of bars that you need depending on the height of the wall and the height of the backfill. These are similar to what's in ACI 332, which is the code for steel reinforced concrete in residential construction, but again, specific to GFRP in this case. All right, so I'll just conclude with a couple of points. First of all, again, GFRP reinforcement is now becoming part of the building code. So if you haven't used it before, if you haven't seen it before, chances are you probably will in the near future because it is becoming more and more common out there in our construction market. The installation of the bars is similar to steel. It is easier, but it does have its nuances that you have to be familiar with if you're out there working with it in the field. And then also the engineering design, although similar to reinforced concrete, it is a lot more involved, but we do have a lot of resources available to help educate you and help get you up to speed on how you design reinforced concrete structures with GFRP reinforcement. And with that, again, I thank everybody for their participation today, and I'd ask Aparna if there's any questions we can answer.
Yeah, we have a couple of questions. Yeah, before going to that, thank you, Will, for delivering an outstanding presentation and sharing your invaluable expertise and insights with us today. So we are a little bit crossing the time, so we might take a few of the questions, but if someone has to leave, it's totally fine. And thank you for Will. He agreed that he will take our questions. So our first question is how the GFRP bars behave under cold weather conditions, like in cold countries where the weather goes below -40 degrees Celsius.
Sure. So there are some specific things possibly relative to fatigue that might be different with FRP reinforcement at very cold temperatures, but in general, those are not very consequential. They're not as consequential with FRP as they are as for, say, steel reinforcement. Remember that a lot of these applications of FRP, like the Boeing aircraft that I showed earlier, these aircraft are flying at 30,000 feet where it is extremely cold, and these materials perform extremely well in those environments. So cold temperatures are not specifically a major reason for concern. The other thing that comes to mind with cold temperatures is that coefficient of thermal expansion issue. So the bars will shrink when it becomes colder. So you might start to see some issues with bond of the bars at very low temperatures. But again, not as much of a concern as when we're talking about the higher temperature end of the threshold.
Thank you, Will. Our next question is, like for the bars, yeah. So we, like in your presentation, you have mentioned that GFRP have non-corrosive property, but will the resin react with the alkaline environment such as waste manure or storage exposures?
So the other environments, the resins themselves perform very well in a wide range of environments, I would say, with the exception of maybe highly acidic environments. Things like hydrochloric or sulfuric acids will attack some of the resins, but they will also attack concrete for that matter. The alkalinity doesn't really affect the resin. What I would say is that alkalinity can affect glass fiber specifically. So GFRP bars, alkalinity can affect the glass fiber that's in the bar. However, the resins do provide protection to the fiber itself. So there's been a lot of studies of the exposure of GFRP bars to high alkalinity. Generally speaking, the polymers that are used are developed so that they do provide protection to the glass fiber in the alkaline environment of concrete. So in general, those applications, again, GFRP performs very well because of the nature of the resins that are used in the bars. And again, that's why the ASTM spec is very specific about the types of resins that are used in these bars. It's really directed at making sure that we do have adequate durability in environments like that.
Yeah, our next question is, how are the GFRP bars used in parking structures if potential exposure to fire is a concern?
It's a great question. So the one area where I've seen GFRP bars used in parking structures is in the top mat of reinforcement. So it ends up being kind of a combination. You have GFRP in the top mat of reinforcement, and you have steel reinforcement or metal deck in the bottom of the concrete slab. The idea there is that the corrosion issue is top down, right? So the chlorides are coming from the top of the concrete, from cars carrying de-icing salts into the garage, and they're migrating downward through the concrete. So having the top mat of reinforcement GFRP is very beneficial. The fire scenario is the exact opposite. Fire is affecting the structure from the bottom up. So as the temperature of a fire increases, the temperature at the bottom of a slab is going to start to increase, but it's going to decrease as you get through the height of the slab. So by the time the temperature reaches a critical threshold at the top layer of reinforcement at that top mat, that takes quite a bit of time. So you actually do achieve fairly high fire ratings because you have essentially very large cover and large protection of the FRP against that fire scenario. So a parking garage application is kind of the best of both worlds. You get steel providing fire resistance and structural capacity at the bottom. You have FRP providing chloride resistance and structural capacity at the top. And so that's, at least in the projects that I've seen, that's where GFRP reinforcement is commonly used.
Mm-hmm. Thank you, Will. So we have talked about cold weather, then fire. I would take this as a last question. So just to wrap up, can GFR be efficient in Middle Eastern countries where the temperatures are very high?
Yes, so there are limitations in the code on the ambient temperature that the bars can be exposed to. The ambient temperature that is recommended is 27 degrees below what we call the glass transition temperature of the FRP, which for most commercially available bars is going to be around 250 degrees Fahrenheit. So the maximum ambient temperature that we're talking about is around 225 degrees Fahrenheit. So over the boiling point of water. So likely not going to encounter that in most normal environments that bars are exposed to. But if you do have bars that have lower glass transition temperatures, so for example, ASTM allows bars to be used that have glass transition temperatures as low as 212 degrees Fahrenheit or the boiling point of water. For bars with lower temperature thresholds, maybe that might become a concern, but we're still talking about limitations on the ambient temperature of up near 180 degrees Fahrenheit. So again, most ambient conditions, you're not going to be getting temperatures quite that high.
Mm-hmm. Got it. Yeah. Thank you, Will. I think we have, I'll just go with the next slide. And
okay.
So thank you all. We appreciate your participation and engagement, and we look forward to seeing you in our upcoming webinars. Please visit aciuniversity.com to see the topics for your upcoming live webinars. And lastly, I want to share with you that NEXT has announced call for ideas for 2024. The ideas can be a problem statement or project statement or project idea or research need that will help to advance the use of non-metallics in building and construction. Please submit your ideas before May 15. You can find the idea submission form on our website, www.nonmetallic.org. Again, thank you for your participation. Also, please remember to fill out our brief feedback survey that you will see as we exit the webinar. If you're looking for continuing education credit and were unable to join us for the duration of the live webinar, be sure to complete the online quiz at aciuniversity.com. Thank you again. See you next time.